Hello. In this video, we are going to cover the fundamental theorem of line integrals. All right. So to start, we're going to start with a vector field. Suppose vector field capital F equals the gradient of lowercase f. So in the last video, we said that this is called a gradient vector field. In this video, we're going to introduce another name that is also common, and that is that we say that the vector field is conservative if this is the case. All right, so F is called a gradient vector field. Or a conservative vector field. All right, so we're going to next suppose that we have a curve. And curve C is defined by either parametric equations, x equals x of t, y equals y of t, or if you combined those definitions, you could form them into a vector function r of t. So that would be x of ti plus y of tj if you did that. And then that vector field is defined from A to B. And so because we have these end values for t, we could take those end values and we could plug them into our parametric equations or our vector function, and we could get endpoints. So we're going to say the endpoints of C are, so we're going to say B is defined by taking B and plugging it in to the parametric equations, and A, same, right? Plug A in. Okay, so the fundamental theorem of line integrals, what does it say? It says that if we had a work integral f dot dr, we could go through and we could rewrite this. This is just by substituting, we get this is the gradient of f dot dr. And then like magic, which we'll have to go through and prove this, but you can jump from there right to going through and plugging the endpoints into our lowercase f here, which we said is called the potential function. In the last section, we said that's the potential function for the gradient vector field. So we're going to get f of x of b comma y of b minus f of x of a comma y of a. And if we used our shorthand, we could just pop this in and say it's f of b minus f of a. Okay, and so that is what the fundamental theorem of line integral says. Is it says that if we have an integral over a work integral over a vector field, and that vector field happens to have that gradient vector field characteristic, then if that's the case, we can go through and evaluate that vector field by just popping the endpoints into the potential function. All right, so let's just make sure that's 100% clear. All right, so the idea is we've got our two-dimensional axis here. We've got a vector field f, which applies a vector at every point. So I'm not going to go through and put the vectors in this time like I did in the last video, but the idea is that there's a vector at every single point. You can go through and just imagine you've got a little arrow at every single point that's on this picture, right, to represent the fact that we have a vector field. Right, so every one of these points has a vector. a little arrow sitting there. And then on top of that, we have a curve C that is tracing through that. All right, so here's curve C, and I'm going to label it right in the middle because I want to be able to put, let's say that here's A, that's the starting point, and here's B, that's the ending point. All right, so what the theorem says is it says that you can go through and you can evaluate f dot dr by just going through and knowing this equals this, knowing that this is a gradient vector field, we can just take the potential function and just pop in the endpoints, f of b minus f of a, like magic. Okay, so does it matter the curve here? The curve doesn't matter. The only thing that matters are the endpoints of the curve. So that's going to have a consequence in a few minutes that we'll talk about, the fact that the only thing that matters is the endpoints. But for now, that's the key, right? So to, given fundamental theorem of calculus, what does it say? Or sorry, fundamental theorem of line integrals. What does it say? All right, it says we can go through and evaluate a work integral by plugging the endpoints into the potential function of the vector field. And that's it. So we just pop in the endpoints and then we're done. And so if you know what the potential function is, then no calculus required, just plugging in. Well, so let's see that in action. Let's see an example. Now, to be clear here, that this is assuming that you know the potential function. Finding the potential function is something that we'll cover later on, but that is going to require calculus to do. But if you knew what the potential function was, then you wouldn't even need to do any calculus, right? So let's say we want to go through and find f dot dr, and we know f equals 3x squared y cubed I plus 3x cubed y squared j. And we know that that happens to equal the gradient of x cubed times y cubed. And then we know that, that equals the gradient of f. So in this case, f is going to equal x cubed times y cubed. You can go ahead and test that by taking the gradient of that. You can go ahead and test and make sure that you do get original. So the idea is typically when we actually do these problems, you're going to be given this and you'll have to go through and find this. But assuming you were just handed it, here you go, then it's going to make the problem really kind of trivially easy if you're just handed the potential function like that. All right, just watch, okay? And then let's say C, we've got C is equal to, you got x equals t, and then y equals t squared. Okay, and then we've got 0 less than or equal to t less than or equal to 1. Okay, so when we're using the fundamental theorem of calculus, what we need, line integrals, what we need is we need to know the endpoints. So we want to go ahead and just plug in to find the endpoints, right? So endpoint B is going to come from taking 1 and plugging it in here. So if you take 1 and plug it in, you're going to get 1, 1, and endpoint A is going to come from taking the other t value and plugging it in, and we get 0, 0. All right, so watch. Okay, so we want to go through and evaluate f dot dr, and all we've got to do is just, we don't even need to go through and take f and substitute it in, and we don't need to go through and find r and substitute it in. Instead, we can just like magic, we can just go through and do f of 1, 1 minus f of 0, 0, which equals 1 cubed times 1 cubed minus 0 cubed times 0 cubed, which equals 1. All it takes is just taking the endpoints and plugging them into the potential function. just like that. All right, so we evaluated our integral f.dr. We didn't go through and take this and substitute it in. We didn't go through and turn this into an r and substitute it in. Instead, we just use the fundamental theorem of line integrals by taking the potential function and plugging in the endpoints and subtracting. Okay. So if what you're thinking is you're like, wow, well, that seems kind of unusual, odd. Why can we go through and do that? Then that's the right thought. All right, so we should go through and prove that we can do that, because that is a very odd result. All right, so suppose we've got f, capital F, and it is a gradient vector field or a conservative vector field. And so you can go through and write it as the gradient of some function. All right, and then suppose we've got C, and C is defined by x equals x of t, y equals y of t, which we can go through and combine to create r of t. Right, and then we also have a less than or equal to t less than or equal to b. So we've got endpoints, and so you can then go through and take a and b and plug them in, and we can go through and find point b. We know that that is x of b comma y of b, and then we can do point a, which is x of a comma y of a. All right, so that's all we need to go through and do the derivation. I think we might need to talk about r of t a little bit more, but let's just jump in, and then we'll see if I need to bring anything more up. All right, so you start off with your work integral. Okay, the next thing you do is you go through and you substitute. Since f equals the gradient of lowercase f, we can go through and substitute that in, gradient of lowercase f dot dr. And then next we can go through and we can actually write out what the gradient is. Okay, so the gradient is it's a vector, and it's the partial of f with respect to x comma partial of f with respect to y. Okay, and then dr, so dr, if you'll recall, that's the derivative of r. So this comes from the last section. If you go back and watch the video, that's r prime. And so r prime, yeah, I guess let me go ahead and write this out. So what is r of t? So if you have parametric equation x equals x of t and y equals y of t, then that means r of t equals x of t comma y of t. It means that you have r of t is a vector function where you've got x of t in the x spot and y of t in the y spot, meaning that if you went through and took the derivative of that to get dr or r prime, you're going to end up with x prime of t comma y prime of t dt. Okay, I hope that makes sense. And then from there, once you've done that, you can go through and at some point here, we're going to go, at this point, we've got t's here. So we want to go ahead and change over from a to b for our endpoints. All right, so once you've changed things over from r to t, you can go ahead and just plug in the t endpoints that define your curve. All right. Now, if you take the dot product of this, right, so this is a dot product. This is a dot product here. Dot product, we multiply component wise, and then we add. So we're going to have partial of f with respect to x. And then I'm going to take some creative license here, and I'm going to rewrite x prime as dx dt. That's the same thing, right? X prime and dx dt, those are the same thing. And then plus partial of f with respect to y, and then dy dt. Okay. And now the reason I did that is that if you went back and you watched the chain rule video from the chapter on partial derivatives, you'll recognize that this thing here, this format, when it's written this way, this is the derivative of a two variable function, x and y, where those variables are defined in terms of t. In other words, it's the derivative of a two variable function where each of those variables is defined in terms of t. So you can go back and watch that video again if you'd like, but this is the most common chain rule definition that we end up using in multivariable calculus. And so it's kind of the whole point of that chain rule section is to go through and talk about this. And so this is the result that you'll get if you go back and take a look. And then at this point, if you go through and look at this, what do we have, right? So we have an integral of a derivative, right? So an integral of a derivative, when that happens, the integral and the derivative cancel. And what we end up getting is we end up plugging in the endpoints into our function, right? So when you go through and integrate, you're looking for you're looking to plug the endpoints into the antiderivative. This is the antiderivative. And so we just want to take those endpoints and plug it in. So we're going to get f of x of b, comma, y of b, minus f of x of a, comma, y of a. All right, oops, not b, but a. Okay, and so I'm going to go over that one more time. So by the fundamental theorem of calculus, all right, so a couple Freudian slips there earlier, because the fundamental theorem of line integrals and the fundamental theorem of calculus are closely related. By the fundamental theorem of calculus, an integral and a derivative, they cancel each other out, and then we take the endpoints here. You take b and you plug it in for t, and you take a and you plug it in for t, and you'll notice that's exactly what I did here. All right, so integral of a derivative, fundamental theorem of calculus, those cancel each other out, and then we plug in the endpoints. All right, and then finally we can go through and x of b, y of b, that is point B, and x of a, y of a, that is point A. And so there's the proof, and so you see we've that's kind of what I've written a bunch of times, that here's the integral of f dot dr is f of b minus f of a, and then f of b minus f of a, where those b and a are points. There's an example where we actually used point B and point A and plugged them in, and so we're being consistent here. Each time, the way that you can go through and evaluate, the way that you go through and evaluate a work integral using the fundamental theorem of calculus, again, it's just by plugging in the endpoints. All right, so the most important factor here is that this has to be true for you to do that, right? If you're watching this and you're like, wait, why don't we just do this all the time? Why did we even learn that stuff in the previous section where we got to go through and plug in for f and do all this, parameterize the curve and plug the parameter in, and why did we jump through all those hoops? It's because that is true in general. This is a specific situation that is a subset, right, of all of the situations. And so we can only do this when we have this gradient vector field, or a conservative vector field. All right, so some consequences, right? So there are some consequences of the fundamental theorem of line integrals that are kind of interesting. All right, so one of those consequences is that curves that are, or integrals that are said to be said to satisfy the fundamental theorem of line integrals are said to be independent of path. All right, so you have this independence of path that goes along with the fundamental theorem of line integrals. So where does that come from? Well, the idea is that if we went through and just said, all right, so let's say we've got f, and it comes from a gradient vector field, lowercase gradient of f, gradient of lowercase f. Suppose we have two curves. So we've got curve 1, which is defined by x equals x1 of t, y equals y1 of t, and that's defined from a is less than or equal to t is less than or equal to b, and we've got curve 2, and that is defined by x equals x2 of t and y equals y2 of t, right? And we know that the endpoints of curve A, endpoints of curve 1, the endpoints are going to be, b, which is x of b comma y of b, and a is going to be x1 of a comma y1 of a, And then curve 2, we have endpoints for that. And we go through and say, okay, that's, is going to be x2 of b, comma y2 of b, and a is going to be x2 of a, comma y2 of a, right? And we know that those are the same, so I can use the same letters, right? So, and so also, so we got curve 1, curve 2, and we know that curve 1 and curve 2 have the same endpoints. Okay, and so we can go ahead and say, b is going to be the point that you get at x1b and y1b, and b is also the point you get at x2b and y2b, right? So visually, if you were going to go through and kind of sketch yourself a little picture, the idea is that you'd have something like you've got, here's a, here's b. So you could say here's curve 1 and here's curve 2. Right? They end up at the same point. Okay, so since f equals, since capital F here equals lowercase, equals gradient of lowercase f, that means that we have the fundamental, we have a situation that satisfies the fundamental theorem of calculus. So we can go, sorry, fundamental theorem of line integrals. It's impossible for me not to say that. F dot dr. We know from fundamental theorem of line integrals, this is f of b minus f of a. And then we also know curve 2, f dot dr equals f of b minus f of a. And so since both of these equal f of b minus f of a, it means that we've got f dot dr for curve 1 equals f dot dr for curve 2. Okay, and so we got the same output, we got the same result, right, regardless of what path we took. Okay, so and you could draw more paths in here. You could go through and say, okay, here, what about this one? What about curve C3 here? Or what about this one? What about a curve that goes, I don't know, something like this? Curve 4. What about that one? Well, if it satisfies the fundamental theorem of line integrals, then the path doesn't matter. All right, it doesn't matter what path you take. You're still going to end up just subtracting the endpoints, and so you're still going to end up with the same result. And so as a result, we say that integrals, work integrals, where we've got a vector field that satisfies the that's a gradient vector field, that's a conservative vector field. We say that those are independent of path. It doesn't matter what path you take, since you're just going to end up subtracting the values at the endpoints, regardless of path. Okay, so that is one interesting result for the fundamental theorem of line integrals. I need to say it like 10 more times correctly after saying it like 4 times wrong. Another result. Okay, what about if C is a closed curve? So we're going to have some closed curves, in this last chapter. So what if we have C as a closed curve? And what we mean by a closed curve? So we mean something, like this, right? So where you've got a curve that's got, a beginning, the beginning and end point are the same, right? So you pick some spot here, this is the beginning point is A and the ending point is B, and those are the same point, right? So you start here, you end up tracing around and you trace your way right back. So if we started A, we ended A. And so you've got A and B are the same. Okay, so what about if C is a closed curve? So if we've got f dot dr over C, and C is a closed curve, right? So we know that f dot dr equals f of b minus f of a. So what is f of b minus f of a going to be if b and a are the same? It's going to be 0. All right, and so we say that the f dot dr, So we say that assuming we've got a conservative vector field or a gradient vector field, and we go through and evaluate the work integral over a curve that is closed, meaning that you've got the endpoint and starting point are the same, then you're going to end up getting 0 out of that. Okay. All right, so those are a couple of consequences that we get from the fundamental theorem of line integrals. So we get that we have path independence, right? And then we also get that the integral over a closed curve is going to be 0. So the next question is, right, assuming that we're actually want to be able to use this as a tool, right? So imagine you want to be able to use this as a tool. So we want to be able to go through and use the fundamental theorem of line integrals to actually do problems, right? And you start a problem, you look down and you got f dot dr, right? And you're like, can I use the fundamental theorem of line integrals here? You ask yourself that, right? Can I use the fundamental theorem? Right? Well, what is required to use the fundamental theorem of line integrals? Okay, what is required? What has to take place? You know, what's the situation? What thing is required? Well, I've said it a few times, and that is that you have to have f has to equal the gradient of lowercase f. So what we need is we need to know whether capital F equals the gradient of lowercase f for some f, because I'm lowercase f. Okay, and so what we're going to do is we're going to introduce a test for that. So this is the conservative vector field test. All right, so given capital F of x comma y, so we've got our capital F vector field. Let's say that equals P of x, y, I plus Q of x, y, j. So we've got P for the x component and Q for the y component. Given vector field F can be broken up into P and Q this way if the partial of P with respect to y equals the partial of Q with respect to x, then F is conservative, right? Meaning then F equals the gradient of lowercase f for some lowercase f. Now, this doesn't give what the lowercase f is. It just says whether there is one. Okay. So I'm not going to go through and prove this. The proof for this is in differential equations. If you're interested in seeing the proof, like right now, you can go to my differential equations lecture and you can go to exact equations. So in my exact equations lecture, I go through and I prove that this is true. You know, if you're a student of mine right now, then and you're taking multivariable calculus, then you're probably going to take differential equations next semester, and you can go and you can learn it. You can learn it when you watch the exact equations video then. So we're going to skip over the proof. We're going to go right to the test. So let's try out the test and see how difficult the test is to use. All right, so suppose we have capital F of x comma y equals y squared minus 2x I minus 2xy j. All right, and the question is f conservative? Meaning, is there a lowercase f whose gradient you could take that would get you this? All right, well, to test for that, what we're going to do is we're going to label this P, label that Q. We're going to take the partial of P with respect to Y. All right, so the partial of P with respect to Y What's that? So that's supposed to be an x there. So the derivative of this with respect to y is 2y. We're going to take the partial of q with respect to x. That's going to be, right, take the derivative of this with respect to x, you're going to get negative 2y. And then the question is, are these the same? Same? And the answer is no. So they are not, this is not conservative. All right. So what does that tell us? It tells us this vector field given here you could not go through and find a lowercase f whose gradient gave you this result. Okay, so this is not conservative, so there is no lowercase f. All right, let's try another one. Let's say we have f of x comma y, and that equals y e to the x minus or plus sine y I, and then plus e to the x plus x cosine y j. What about this vector field? Is this vector field conservative? Meaning, is there a lowercase f whose gradient would give us capital F? All right, well, to go through and test that, we'll label this p, label this q. We take the partial of p with respect to y. The derivative of this with respect to y is going to be e to the x. The derivative of this with respect to y is going to be plus cosine of y. The derivative of q with respect to x, we differentiate this with respect to x, we get e to the x. Differentiate this with respect to x, and we're going to get cosine of y. And then are these the same? Yes. So f is conservative. Okay, so that's all there is to going through and doing the test. So then, okay, so that's the next question, right? So let's say you've got f dot dr, and you're saying, you ask yourself, well, I'd really like to be able to go through and use the fundamental theorem of line integrals on this. So the first thing you ask yourself is f conservative? Well, we've got a test for that. And then the second thing, you've got to go through and to use the fundamental theorem, we need to be able to find lowercase f so that gradient of lowercase f equals capital F, right? If we had that lowercase f, then we could go through and do f of b minus f of a, right? Where a and b are the endpoints of C. So we could just pop in b and a if we had that lowercase f. So that's going to be the next step. So you go through and you start off with your work integral here, and you're like, oh, I'd really like to use the fundamental theorem of line integrals. The first thing you ask yourself is, well, is it possible? Is this conservative? Does it have a lowercase f whose gradient would equal it? And that's when you use the test. Use the test to figure that out. And then once you find that it does, then the next step is, okay, well, now I need to find that lowercase f. So how do I go through and find that lowercase f so that the gradient of that lowercase f equals capital F? Because once I've got the lowercase f, then I can pop in the endpoints. But it's not going to be just given to you. I mean, it is in this lecture, but it's not, in general, it's not going to be, you're going to have this, and then you're going to have to go through and find the lowercase f. So how do we do that? All right. Well, one of the things that you can do is you can go through and you can say, what is capital F? Capital F equals, let's say it's P I plus Q J. That's what we just said, a few minutes ago. What is the gradient of lowercase f? It's the partial with respect to xi plus the partial with respect to yj. Okay, and then if you go through and just take these and line them up, what we've got is that P equals, actually, let's do it the other way around. We've got that the partial of f with respect to x equals P, and the partial of f with respect to y equals Q. All right, so what we need to do is we need to go through and find the lowercase f, so that this is true. If we do that successfully, then we will have found the vector, the lowercase f, whose gradient equals capital F. Right. So we just need to find the f whose partial with respect to x is p and whose partial with respect to y is q. And if it seems like you need more information than that, you don't. It's not as hard as it looks. So let's go through and try one. You don't even need a lot of space. All right, so let's start off. So we're given capital F. So we know that capital F equals 3x squared yi plus x cubed minus 3j. All right, you go through and you test this and it tests out. Yep, it is conservative. There is a lowercase f whose gradient equals this. How do we find it? All right, well, we take that lowercase f and we say the partial with respect to x equals p, which is the thing that's times I, and the partial with respect to y equals q, which is the thing that's multiplied by j. All right, so we want to go through and find the f that makes this true. How can you do that? All right, well, what we can do is we can get at the lowercase f here by getting rid of the partial. Right, so what this says is it says that we took a function and we differentiated with respect to x and got this. Well, in our toolboxes, we know how to reverse derivatives. They're called integrals, right? It's the indefinite integral. So we could go through and find f by getting rid of that partial with respect to x by integrating with respect to x, right? Does that make sense? So if we've got a f that's partial with respect to x, if we integrate with respect to x, the integral and the partial will cancel, and we can just pull out capital F. So if you write that out, we're going to go through and integrate 3x squared y with respect to x. And if you do that, you're going to get x cubed y plus c, right? So this is an indefinite integral, so we've got that plus c. Now here's where things get a little strange. Okay, it takes a little bit of getting used to, right? The plus c, what it represents in regular calculus, Calc 1, is it represents a constant. The constant that would go away if you differentiated this with respect to x to get what's inside the integral, right? What is the integral finding? What is this saying? Is it saying, tell me the thing that I would differentiate to get 3x squared y? Well, that thing would be x cubed y plus some constant stuff. And then if you differentiated it with respect to y, the constant stuff would go away. So the constant is there to represent that constant stuff that would go away. However, with multivariable functions, that constant stuff could have more than just constants in it, right? If you're differentiating this with respect to x to get what's inside the integral, then you could have had y stuff here, right? Let's just do an example here, right? So suppose this was plus y squared, right? If this were plus y squared, if you differentiated this with respect to x, what would happen? The derivative of this part with respect to x, you treat y as a constant. The derivative of this part, you'd get 3x squared y. That's this. The derivative of y squared with respect to x, right? You're treating y as a constant. The derivative of y squared would be 0, and so y squared would go away, right? And so that plus c of y, it represents the y stuff that would go away if you differentiated this with respect to x, right? And so anytime you integrate with respect to x, and you write out a constant term, the constant term could also have not just 1 or 5 or 17, not just constants in it, but could also have y stuff in it. Okay, so with that said, once you've done this first line, you go through and write this out. To go through and figure out whether there are any y's inside there, what you're going to do is you're going to take this definition that you've created for f, right? This gives us a definition for f, and you're going to differentiate it with respect to y. If we differentiate this with respect to y, we get x cubed. And then if we differentiate c with respect to y, so c is just a function of y, the way that I've written it, you're going to get c prime of y. Okay. And so once we've done that, we've gone through and we've said, you know what, our definition that we just got for f by using this guy here, if we use that, it gives us this definition for the partial of f with respect to y. Well, look here, we've got another definition for the partial of f with respect to y. So what you can do is you can combine those by setting them equal, and something cool happens, right? The x cubes cancel, and we get that -3 equals c prime of y. And now if we want to go through and figure out what we want is we want c of y. We don't want c prime of y. We want c of y. And so what you can do is you can go through and integrate both sides of this with respect to y. And then the antiderivative of -3 with respect to y will be -3y. And then the integral of the derivative of c with respect of c of y is going to be just c of y. The integral and the derivative cancel, again, by fundamental theorem of calculus. Now, if you wanted to be totally complete here, there's another plus something, a plus constant, because there could be a constant in here. But we're just going to ignore the constant. Now, there's a reason for that. It's that if you did use the constant in the fundamental theorem of line integrals, then the constants are going to end up canceling when you go and plug in the endpoints. Okay, so when you go and plug in the endpoints here and here, you can imagine if I put a f of b and I had a +5 here and a +5 here, if I had constants on both of these, those +5s are going to cancel because you're subtracting. Right, and so because of that, we don't care about the constant because it's just going to end up canceling when we actually use the fundamental theorem. Now, if you weren't using this for the fundamental theorem of line integrals, then maybe you'd want to put in the plus constant. But in this particular case, you don't need it. So that's why I'm leaving it off. Okay. Anyway, but to finish the actual problem, once you've found that c of y equals -3y, you then take it and you plug it in back up here. And I guess we do need a little bit more space. So that tells us that f is going to equal x cubed y. And then what is c of y? Plus c of y, it's -3y, so we get -3y. All right, and that's our f. And you can go through and test that, right? Take the derivative of it with respect to x, and then see if you get 3x squared y. Take the derivative of it with respect to y, and see if you get x cubed -3. If you do, the derivative of this with respect to x is this, and the derivative of this with respect to y is this, then the gradient of this function equals capital F. Right? That's what the gradient is. The gradient of this is the derivative of this with respect to x times I, the derivative of this with respect to y times j. Okay. Oh, I almost forgot. All right, so I did forget. So what the other thing I wanted to do with this problem is I actually wanted to use the fundamental theorem of calculus on it, not just go through and find. I did it again. We want to use the fundamental theorem of line integrals on it. Not just go through and find the lowercase f, but actually use it so you could see how these problems could work in their entirety. So with that in mind, let's just kind of take a step back and start over again, right? So suppose you're told to go through and evaluate f dot dr. All right, you're told that f equals 3x squared y I plus x cubed minus 3j. And you're told we've got c, and c is defined by r of t equals cosine t, not cotangent, cosine t, comma 2 sine t, where 0 is less than or equal to t is less than or equal to pi over 2. All right, so and so we're asked to go through and evaluate this. We could go through and try and evaluate it using the methods from the previous section, but we want to use the fundamental theorem of line integrals. Line integrals. I actually have to think about it to say it correctly. And so if you're going to use the fundamental theorem of line integrals, then you need to go through and take the endpoints and plug it in. You take the nt values and plug it in to get the endpoints. So we're going to have r of pi over 2. All right, so this is going to get me point B. That is going to equal cosine of pi over 2, comma 2 sine of pi over 2. Right, and so cosine of pi over 2 is 0, and sine of pi over 2 is 1. 1 times 2 is 2. All right, and so we're going to get the vector So for B, we get the vector 0, 2. That just means that we end up getting the point 0, 2, right? So the vector here starts at the origin. And if you have a vector that starts at the origin that is 0, 2, then it terminates at the point that corresponds to the vector. All right, so this tells us that B, actually, let's just do it this way. Thus B is 0, 2. All right, and then R of 0 equals cosine of 0, 2 sine of 0. And so cosine of 0 is 1, and 2 sine of 0 is 0. So we get 1, 0, and that tells us that A is 1, 0. All right, and now we can go through and actually evaluate this by using the previous result that we got, right? So we went through, and the previous result we got is that lowercase f here is our potential function. It's our function that we can take these endpoints and plug into. So this is going to equal lowercase f of 0, 2 minus lowercase f of 1, 0. And then that lowercase f is what we just got, which I already forgotten what it was. So it's x cubed y minus 3y. So we're going to get x cubed y minus 3y. So x cubed, so we're going to get 0 cubed y minus 3 times y, right? And then we're going to get x cubed times y minus 3 times y. All right, and if we simplify that, so we're going to get, looks like minus 6, and then that's all 0, so we're just going to get minus 6. Okay. And so we could go through and that would be an example beginning to end of using the fundamental theorem of line integrals to go through and evaluate the work integral. All right. So to do it, you need to go through and you need to do this process, though. We did end up using that in the problem. So it's used right here. So you do need to go through and do that part where you have to go through and find the potential function for the vector field that you were given. All right, I guess the one thing that I didn't show is we didn't go through and verify that this is conservative. You know, we didn't verify that it has a lowercase f whose gradient is capital F. You know, we didn't verify that it has a potential function lowercase f. We skipped over that step, but other than that, this shows pretty much the whole process. All right, so let's see it all in its entirety from beginning to end without, you know, me forgetting to, you know, introduce it, and you know, hopefully that might help. All right, so let's say we've got capital F. It's equal to y squared z cubed I plus 2xy z cubed plus 2z j plus 3xy squared z squared plus 2y plus 2z k. We're given curve C. C is the line segment from 1, 0, -2 to -1, 1, 0. Okay. And then we're told go through and find f.dr over C. All right, and we're told to use the fundamental theorem of line integrals. So it's not an option to go through and use the methods from the last section to do it. All right, so you don't want to go through and actually find the formula. You know, you want to go through and find the formula for the line segment here. You don't have to do that. That's the method from the last section. That's the method for evaluating a work integral from the last section. In this one, we just want to go through and use these two endpoints. And so the fact that they just gave us the endpoints, we're like, cool. We don't have to do any work to go through and find them. Like the last one, we had to actually plug in the t-value to find them. This makes it so that there's no work at all to go through and find the endpoints. They just gave them to us. All right. But we still do need to do something here, because to use the fundamental theorem of line integrals, we need to have that lowercase f, that where we can take these endpoints and plug them in. We need to have the potential function. We need to have the function whose gradient equals this. Okay, so how do we find it? All right, let's go through and just mark off some space here. All right, so what you want to do is you want to go through and take the partial with respect to x and set it equal to the component that's times I. That's y squared z to the third. Take the partial with respect to y, set that equal to the part that's times j. That's 2xyz cubed plus 2z. Take the partial with respect to z and set that equal to the z component. We get 3xy squared z squared plus 2y plus 2z. Okay. So once you've got those written out, what we want to do is we want to unpeel this, to get it at the underlying f. And I showed how to do it a couple pages ago. To unpeel a partial with respect to x, you want to integrate with respect to x. So we're going to have f equals the integral of f differentiated with respect to x integrated with respect to x. So the integral with respect to x and the derivative with respect to x will cancel, getting us at the underlying f. All right, and so if we do that, we're going to get integral, pop in y squared z cubed dx, right? And then what are we going to get? We're going to get the antiderivative. This is going to be x y squared z cubed plus c. And then what c? Let's think about it. What c stuff could be in here whose derivative would end up going away? Like they would act like a constant, right? So if we had, since we're differentiating here with respect, integrating with respect to x, that means we're going to differentiate with respect to x to get back up. And so we're going to differentiate this with respect to x to get y squared z cubed. So what could we have here whose derivative with respect to x would be 0, that would go away, right? And then the answer is we could have y stuff, right? If this was y squared, the derivative of y squared with respect to x would be 0 and it would go away. We could have z stuff. The derivative of z squared with respect to x would be 0 and it would go away. And we could have a combination of the two. Okay, and so instead of just putting a c of y here, we need to put a c of y comma z. All right. And now to figure out what's inside that c, what we need to do is we need to take this and kind of use it as a definition, use it as a starting point, and then differentiate it with respect to y, and we'll end up getting this other guy, and we can compare them to figure out what's in that c of y. So if we differentiate this with respect to y, what's going to happen? We're going to get 2x y z cubed, and then the derivative of, since this is a multivariable function that has y's and z's, if you differentiate with respect to y, it's got to be a partial of c with respect to y. And once we have that, we can match it up with the actual partial with respect to y that we have, and we'll get 2xyz cubed plus 2z equals 2xyz cubed plus the partial of c with respect to y. These cancel, and you get 2z equals the partial of c with respect to y. And now we want to get at c. To get at c, we need to get rid of this partial with respect to y. How do you get rid of a partial derivative with respect to y? You get rid of it with an integral with respect to y. So we can integrate both sides with respect to y. The antiderivative of 2z with respect to y is going to be 2z plus c, and the antiderivative of c, the partial of c with respect to y integrated with respect to y, the partials and integrals are going to cancel, and you just get c. Maybe bad choice to have c twice here. Let's use d instead. Let's use d there. Okay, and now, so here's the thing is when we went through and we integrated this with respect to y, Okay, so we said that C could have Y or Z stuff in it. All right, so we said it could have C, Y, or Z stuff. And so if you go through and you find the antiderivative of this with respect to Y, you're saying that if I differentiated this with respect to Y, I would get 2Z. Is there any what stuff could we have here whose derivative would end up going away if we if we differentiated with respect to Y? Well, not Y stuff, right? If we had Y stuff here and we differentiate it with respect to Y, it should still be there. So not Y stuff. We could have Z stuff, right? You could have a plus 5Z here. And if you went through and took the derivative with respect to Y, actually, hold on. This is not right. This whole time I'm like looking at that. I'm like, that looks strange. If we integrate 2Z with respect to Y, what do we get? 2zy. There we go. And so the derivative of 2zy with respect to Y is going to be 2Z. But what about 5Z? If we differentiate 5Z with respect to Y, it would be 0. So we could have some Z stuff here that ends up going away. Okay, and so you do need to keep that there. All right, for the problem. And it makes sense too that there should still be something left because we have this third definition. This third definition is going to enable us to figure out what Z stuff is in there. All right, and now so here's where things start to get a little bit messy. So what we need to do is we need to take F, and we need to take this result we just got, and we need to combine them, and you're going to get that F equals x y squared z cubed plus 2zy plus d of z. All right, and then finally, to go through and use the last definition, we're going to take the partial of this with respect to z. That's going to give us 3xy squared z squared plus 2y plus d prime of z. I'm using prime here because I'm differentiating a single variable function with respect to that variable. And so you can use a prime there instead of a partial. Right, so if we differentiate C with respect to Y, there's two variables here, so you need to do partials. But if you differentiate D of Z with respect to Z, then you can just go ahead. It's the same variable, and so you can just use a prime. All right, and so once we've got, that's our definition for partial of Z that came from, going through and unpeeling stuff, and we need to compare it with the actual partial of F with respect to Z. So if you go through and set those equal, we get 3xy squared z squared plus 2y plus 2z equals 3xy squared z squared plus 2y plus d prime of z. All right, and then look at that. This cancels, this cancels, and you get 2z equals d prime of z. All right, and since we want to know what d of z is, to get rid of the prime here, this prime was differentiating with respect to z, so we need to integrate with respect to z to reverse that, integrate with respect to z. And if we do that, you're going to get z squared equals d. And again, just like a few minutes ago, technically there should be a constant in there, a plus e or something. But when it comes to using the fundamental theorem of integrals, fundamental theorem of line integrals, the constant would end up canceling because we're going to end up subtracting the endpoints. And so we can just ignore the constant. All right, so now finally, so taking that z squared for d and pop it into this definition, and we're going to get our final result. And there's kind of room right here. I guess I get right here. So we're going to get xy squared z cubed plus 2zy plus z squared. All right, and so that's the definition that we're going to end up getting for F. And you can go and check that if you want. Go and check that if you do go through and take the partial of that with respect to X, you get this. The partial of that with respect to Y, you get this. And the partial of that with respect to Z, you get this. Okay, and that's the goal, is we're trying to find the thing whose gradient would end up being this. Right, so once we have done that, we can go through and evaluate our fundamental theorem of line integrals by just doing f of b minus f of a. All right, and what is b? It's going to be f of, All right, so it goes from here to here. So that means B is the -1, 1, 0 minus F of 1, 0, -2. And now we're just going to use our F that we just spent so much time working out. So we're going to have -1 times 1 squared times 0 cubed plus 2 times 0 times 1 plus 0 squared. That's this minus parentheses. Then we're going to have 1 times 0 squared times -2 cubed plus 2 times -2 times 0 plus -2 squared. All right, so what is that? So that's 0, that's 0, that's 0, that's 0, that's 0, that's 4, so -4. All right. And that's it. That's how you go through and use the that's the basics behind the fundamental theorem of line integrals. Line integrals is is basically this was covered in this video. Okay, so just to recap, so you can go through and you can evaluate work integrals. Work integrals have to look like this. You can evaluate work integrals by going through and just using the endpoints if the vector field is conservative. If the vector field is a gradient vector field, meaning if there is a lowercase function whose gradient equals capital F. Right? To test whether that's true, there's a test in the video. You got to go through and you've got to take the partial of P with respect to Y and compare it to the partial of Q with respect to X. If that's our test to figure out whether the capital F is conservative, whether to figure out whether the capital F has a lowercase f with those characteristics. So you got to go through and use that test. And then once you've used that test and you know that there is a lowercase f, how do you find that lowercase f? Well, so I detailed the method here with 3 variables, and then I detailed the method here with 2 variables. Okay, so it's either 2 variables or 3 variables. And so those are how you go through and find that lowercase f. And then once you've got the lowercase f, you just plug in the endpoints and subtract and you're done. Okay, so that's the video. Thank you for watching. See you next time.